Hello and good morning, everyone from Bangladesh, and good day to all of you, wherever you are joining from. So this technical session 4, application of technologies in meteorology, we are still awaiting for our other participants and panelists to join. But in the meantime, what we can do is actually we can introduce our session chairs and co-chairs. So in this session, we have four presentations coming up, and the session will be chaired by Professor Dr. Toru Terao, and also session co-chair for this session is SM Kamul Hassan sir from BMD. So just a quick reminder to the panelists and all the participants as well, is that this session, within the session, the panelists can avail all the usual opportunities in Zoom, like sharing video, sharing screen and everything else. But the participants just remain silent, and if you have any questions, just raise your hand and we will let you talk. So over to you both, session chair and co-chair, sir. Thank you. Both Terao sir and also Kamal sir, you can proceed with the session now.
So now all the participants are there here. Can we begin or should we wait? Can you hear me?
Hello, sir. This is Kamal
Yeah.
Hassan. I think, yeah, we have 1 minute. So after 1 minute, we can start. Our keynote speaker is already joined.
I see. Okay. Then we may.
But others should be joined. Otherwise, it will be difficult to continue.
Okay. So we can wait some more. Okay.
Yeah.
Yep. Thank you. Nice to meet you here.
Yes, that was after a long
time. So yeah.
After a long.
Yeah, very tough.
So where is Murata-san? She should join.
I think so. So we are discussing about this session last night or so. So she's talking about this. So she have to be clearly aware about that this session. What time it begins? So she has to come soon. Okay.
Sir, Dr. Burata madam has joined actually.
I see. She's here. Okay. So the first speaker also here, and the third and fourth speaker is now waiting for them.
The fourth speaker, Dr. Elizabeth Page madam is here. I think Dr. Paul would join within the session. So maybe we should start, and when he joins, I will let him all the opportunities to talk and share.
Okay, then
yes, it is better.
We can wait some more. Okay, yeah.
Terasan, actually we can start now, and I hope within 40 minutes, after 40 minutes, the remaining participant will join.
Okay.
Otherwise, there is time limit, so we have to.
Yeah, we have to finish by 10:40 maybe. So Okay, then can we
Yes.
start now? Okay. Thank you very
Yeah.
much. And thank you for everyone to coming to this session. And the title is the application of the technologies in meteorology. And so it's very important for the worldwide climate. And so it have to be so much important for the people's life. And they are now changing so much. So I think it's a very important session. So I'm very happy to be here. So now we can begin from that first speaker, okay? And I'd like to introduce some of the first speaker now. And the first speaker is Dr. Nachiketa Acharya-san. So he's a statistical climatologist with specialties in statistical and machine learning modeling in climate science. And he's now currently serving as an assistant research professor at Earth System Modeling, Analysis and Data at the Department of Meteorology and Atmospheric Science in Pennsylvania University. So now we can have his talk, and his title is the Machine Learning Framework for the Prediction of Bangladesh Summer Monsoon. Can you start now? Okay.
Sure, thank you. Let me try to share my screen.
Okay.
Is it visible in a full presenting mode?
Yes.
Okay.
You can proceed.
Thank you. Thanks to organizers, especially Saurabh and the team, for giving this opportunity, and thanks for making in my time. So today I'm going to talk about ongoing work, which is like extension of our past work with BMD, especially Dr. Kamrul Hassan's. So we have done a little bit of work on next generation seasonal forecast in a couple of years. So now we're moving to a machine learning framework for how to predict Bangladesh summer monsoon using some state-of-art method. And I want to acknowledge my colleagues, Kyle, Carlo, and obviously Dr. Hassan. So a little bit of history, like whoever not familiar with this seasonal forecast business. So mostly there is two methods. One is statistical method, one is dynamical methods. So especially for the Bangladesh monsoon, like if you go to the literature review, you can find kind of time series forecasting method, like where people are actually using some auto regression kind of model from past data and try to predict future, or mostly like a ENSO based forecast, like correlation based, like what is the like using a teleconnection of ENSO and making some regressions. So those are very popular in literature, but those methods has a huge limitations. One is the autocorrelation of rainfall is very poor, especially recent years, and the teleconnection between ENSO and others large scale circulation with the Bangladesh monsoon is changing because of the global warming. We all know about that. So the alternative is physical process based general circulation models, and we all know nowadays like how important to have some physical process based models. Although they have some limitation. So one of the limitation is that not one single model could have the answer what we're looking for. So we need a multi-model. A quick example again, like let's say an example of 2009 Indian monsoon, which was a very significant drought year, and these are the forecasts from some general circulation model in month of April, and those are the picture we get. So in the month of April is very tough to get a decision like which model we should believe, because every model has different scenario. But at the end of the monsoon, we get this thing. So that means we understand that what is the importance of a multimodal ensemble in real-time operational focused. So on that note, we are actually working in this problem. So there is some traditional method of multimodal ensemble. One is just equal weight. You just give the average, or you can actually give the weight based on their prior performance in the hindcast or past forecast. And most of like the one method is very popular, which is called multiple linear regression. That means you're kind of regress 4-5 model, whatever you have, and the observation in the past using the same relationship and try to predict in the future. So on that note, I'm thinking about whether machine learning can improve this whole multimodal ensemble system. because machine learning can give us some added value. So on that question, we started with thinking about like, let's use the machine learning as a tool of multimodal and give the same input and then output something like that. So the question is like, should we use machine learning because machine learning is very buzzword nowadays? The question is not. So I was working on machine learning since 10 years now. So my journey was very interesting as I am a statistician, so I don't have much background of machine learning. So for me, it was very, kind of sci-fi movie, like it's robotics things. But when I start exploring the machine learning, the first thing comes is like a black box. Nobody understands what's going on inside. And it's very important for a modeler to understand the model itself, otherwise we cannot customize. So I start, reading the papers and talking with different people. And I have a very interesting example. I just want to, give this analogy, like there's a story, like there's some blind man and everybody wants to feel or touch elephant and try to say how the elephant look like. And everybody has their own opinion. Same thing happened with me whenever I started talking with the people from climatology, hydrometeorology, agriculture. They are defining machine learning in different way. So after doing a kind of self-study, I kind of understand like machine learning is like a spider net. It's not like one method, one subject, it's a huge. But if I kind of simplify the whole thing, like it is a learning, right? One is supervised learning. That means we need a teacher and teacher will tell us which is good, which is bad. And another thing is unsupervised learning. That means you are learning from the data. So you're learning for yourself. You don't have any teachers. So going back and try to connect my statistical knowledge, and I found the linear regression is itself a very simplest form of machine learning. So machine learning is always there, but I could not understand. So now I understand. So it's like machine learning is learning from a relationship of data. So anyway, so it's an interesting story. So on that note, very important to find it out which method could be good for the problem. So the problem we have, it's a very simple regression problem because we have some climate models. You can think about predictors and we need a predictant. So the first question is what kind of machine learning method we should choose. And I found like there's two kind of method we can go. One is decision tree based methods and one is artificial neural network, because both of the method has that regression approach. So on the decision tree, it has a a long story, but it's actually, if we can classify in two method, is actually bagging and boosting. Bagging means you start with some random decision and you kind of resample in your data, and then you randomly select some features independently and make some different trees, and at the end you aggregate. And another one is like boosting. So you make one decision, based on that decision you again to the other decision to actually reduce the error. So there's a different kind of things, but not going to too technical. The method we choose here, we call random forest, which is very popular nowadays. The reason I choose the random forest, because it, as I said, like it has a different independent decisions and independent idea based on the same data. And it's random because it's a randomly resample and randomly chosen the features. And at the end, you just take the average of all the decisions. So that's the random forest. Another neural network kind of method, like we know, like neural network inspired by the brain, how brain understand or brain release the information through the neurons. But one like very popular method is like people use called single hidden layer feed forward. That means you start with some random weights with the decision and go through different activation function. Then you look at your cost function, then you go back and update the weights and do that. So it's a long journey, and sometimes it could not be used for real-time focus because you need lots of data, and also you need a long computational time. So keeping those constant in mind, we try to choose a very generalized format of single layer fit forward network, which is called extreme learning machine. So the difference between extreme learning machine and traditional neural network is like it's not everything is random there. There is some part we can control and some part chosen. So anyway, so based on these two different family of machine learning, one is brain inspired method and one is decision tree inspired method, we kind of do this experiment. So we took a data set from 1982 to 2018 using all North American multimodal ensemble, which is a very state-of-art coupled climate model. And we also use the very state-of-art observation, which is prepared by BMD, and that's the best data set up to now for Bangladesh. Is 5-kilometer resolution. It's a merging between satellite data and the real-time station data. And we also use the benchmark method, which is ensemble mean and MLR or multiple linear regression. In literature, it's named as super ensemble. Then you do different pre-processing of the data and how to control those features in machine learning. So it's lots of technical things, or not going to go too much detail, but we are actually running 1,000 times for each machine learning in a live on out cross validation, because we don't have much data set. So we cannot just divide the test and train. So rather we have to use all the data and leave one out data every time and make those things. On that note, you can just show your preliminary results. So this is the index of agreement, which is a modified version of RMSE, but it has a bound 0 to 1. So you can see the simple improvement of machine learning compared to average and linear regression. We also plot the Spearman rank correlation, which is give us the pattern. Obviously, you see that this is like always a tough to improve, but at least compared to the simple linear regression, the things are improving. Because when you look at the ensemble mean, there's no at all a pattern capture from the models. So anyway, we kind of looking in different skill score right now and try to understand the robustness, because there's always a chance in machine learning you are ended up with overfitting. That means in the past case, maybe you have an excellent forecast, but when you real-time forecast using this method, it will be failed. So we are right now testing for the real-time forecast for couple of after 2018 years. So on that note, that's the thing. But another thing I want to mention that, although the machine learning things are is interesting, but it's very tough to implement. And you understand that things, and not every package in Python and R or MATLAB, it's like ready-made. So me and my colleague Kyle actually working on a new tool, it's called XCast, where, it's already in GitHub and, it's already in Conda. So this method is actually helping any kind of climate scientist people or other people who don't have this background. It's very simple to implement and use, and you can play different kind of games using either in like one grid point data or spatial data. So it's a very good tool, and I encourage if somebody have interest to look at this, and you can try with your own data set. It's not only for the multimodal, you can also use for different kind of climate prediction. On that note, I just conclude that yes, there is a significant improve for the machine learning based multimodal, and we have a Jupyter Python notebook so people can use it, and a couple of reference in the past paper we published, and also the paper on the data set we describe here on the BMD. And on that note, I said thank you very much, and ready for any comments or feedback. Thanks.
Thank you very much. So thank you for keeping your time. So now it's open to the questions and comments. So do you have any comments or questions? So please raise your hands, or just speaking from your microphone, or you can put some questions, comment to the chat system also maybe.
Terasan, I have one question to Dr. Acharya. Not question actually, just few clarification. Actually, Dr. Acharya is working on seasonal forecasting long before, and to him, I am asking that he is also working in subseasonal forecast. So, Dr. Nachiketa, this process, this tool is using in subseasonal forecast also.
It's a very good question, Dr. Kamrul. Yes, so the tool we made is very generalized tool. So it can be used for any kind of climate problem. It can be used for subseasonal, it can be used for seasonal, it can be also used for cyclone forecast, for if you're interested to have a seasonal cyclone forecast, you have a data. Or if you're interested with very traditional ENSO based forecast, you can also use it. So we don't make this tool for a particular case. It's for just like another package. And we provide some example notebook. Like, okay, if you want to use for multimodal, that's the way you can do it. If you want to use for other thing, you can also do it. So it's a very general. And actually, I just want to mention here, like 2 months back in S2S project, there is a competition called EIML prediction, and we actually use XCast, and we actually use a different method, not this ELM here. We use POELM, which is probabilistic ELM, and we use the same tool there.
Thank you.
Thanks.
Yeah, thank you very much. So yeah, I also very much interested in the seasonal forecast because I'm very interested in the ENSO impact itself. It's a very long history of research, but not solved yet. And so recently, they say that the correlation have to be there, but it is also changing in time according with maybe the climate change. So is this method can adapt for this type of change in the correlation between these systems? It's easier to, yeah.
That's an interesting point. Yeah, exactly. Like, what we found in our study, like the correlation between ENSO and like Bangladesh monsoon was negative. But if you look at very recent data, it actually changed the sign, although it's not significant. So like doing this kind of regression, one thing we have to take care, like the non-stationarity of the relationship. Like most of the regression is like kind of very basic assumption of that things are not going to change in future. So on that note, if we use the machine learning plus regression, we can actually add this non-stationarity trend impact there, and we can use it. As I mentioned, this tool has so many different, for example, I just to show 2 of the method because that works for this particular problem because I'm dealing with regression. But this tool also have other methods which can also deal with some train analysis and non-stationarity things. But yeah, no, that's a very valid point, and that's something like people are, especially on the temperature forecast, if you look like the model also have the trend, the observation also have a trend, but those trends are not same. So how to incorporate the trend while you actually correcting the models or doing the multimodals? Or same thing, like how to incorporate the recent information of ENSO teleconnection. There's a very valid research question. People are working on that, including me. So yeah, so that some of the method we include in this tool can also work for that. Thanks for the questions.
Thank you very much. So now we have another question from Dr. Mahmood. So can you speak now?
Yeah, hello. Hi, Dr. Nanti. That's a very nice presentation. Really like the way you present. So you can hear me, right?
Yes.
Okay. So for the machine learning framework, so do you have any, like you showed the index of agreement and another performance matrices, I would say. So do you have any other matrices that you have used, like ROC curve or any other in general machine learnings results that can be shown in there, like in the study that you did?
Yeah, that's a very good point, Suhail. Yeah. So the point, like the way I choose these 2 particular method because I want to show the error and the pattern. But you're right, like if I want to show this heat and falls, I should show the ROC. If I want to show some kind of reliability of my forecast, I can show the the reliability diagram. But the good thing is here, like we actually include all those skill maps or skill scores in the tools. So people can generate all those things. So just the brevity of this talk, I just put these 2. But you're so right, because you should look all the dimension of the skills, not only 2. So, and also one thing I want to mention that I just present here the deterministic forecast, right? I'm not presenting a probabilistic forecast, but for the seasonal forecast, the probabilistic forecast is so important. So in that tool, we are actually incorporate some of the probabilistic forecast, like how to convert this deterministic forecast in a probability, because there's another problem in machine learning. Like most of the machine learning can work very well for the 2 category forecast, like classification, whether it's cat or dog, right? But in seasonal forecast, we have so many things like 3 category, 5 category. So we kind of customize the the activation functions such a way that it can actually produce the multi-level forecast. So the things are there, but obviously I'm not showing everything today, but I encourage everybody to look at that tool and, explore more. Thank you, Suhail.
No problem. It's a very, interesting, product to look at. I'll definitely get back to you with the feedback.
Sure, Suhail. Thanks.
Thank you very much. Now we are not approaching the time limit, but you have any question in short time? You have? Okay. Okay.
Yeah, I just can't resist myself. This is not a question, actually. Thank you, Dr. Nachiketa, for your presentation. But I'm very interested in working with HOS and all those things. So if I may ask you to, guide us through this process, would you please, would you mind?
Obviously not, but can I, because I can't see your name here, so.
I'm actually Saurabh.
Oh, Saurabh, okay. Yeah, sure, Saurabh, why not? Yeah.
Okay, thank you.
Yeah, thanks.
Thank you very much. So it's a very important new method for us, and it's very practically very nice tools. I think I try to adapt to your method also. Thank you very much.
Sure.
And thank you for your many questions, but I have to move now because of the time limit. Sorry.
Yep.
So please type in to chat system like that. Thank you very much. And now can we move to the next speaker? So next speaker is Dr. Mie Murata. I know her so much. And she's a lecturer in the Kochi University in Japan. And she's now working on the so high rainfall area in northeastern part of the Indian subcontinent, like Cherrapunji and the Meghalaya Plateau. So can you start?
Just a moment. How to share my slide?
Maybe you have some green button in the bottom or
Okay.
yeah, okay.
Okay.
Okay, coming, yeah.
Yes, Murata-san, it is okay.
Thank you, Hassan-san. So, okay. So my name is Fumie Murata from Kochi University, Japan. I would like to talk about initial analysis of Cherrapunji C-band radar in the Meghalaya Plateau during July to August 2019. Our Japanese group have been conducted rainfall studies over Meghalaya since 2004. The southern slope of the Meghalaya Plateau is known as a heavy rainfall place. The rainfall is fully orographic. The scenery of the place has steep cliffs and deep valleys, as you can see at the top left photo of this slide. The shade of the right figure is altitude, and the center of the circles is Cherrapunji town. This town has a world record of the rainfall amount for more than 1 month and longer time scales. The left bottom figure is annual rainfall during 1851 and 2013. The average rainfall is around average annual rainfall is around 12,000 millimeter, and it includes 2 years, which exceeds 20,000 millimeter. On 2016, Indian Space Research Organization started the C-band weather radar observation at Cherrapunji. This is the objective of this study, to know the mechanism how heavy rain precipitate. It's important to plan a strategy to mitigate rainfall related natural disasters over the world. The southern slope of the Meghalaya Plateau provide a unique observation field to study heavy rainfall. So here we analyze the new Cherrapunji radar data during July and August 2019. It's a 2-month data that was provided by ISRO and JAXA-ISRO research collaboration. Weather radars can provide the unique data about what happens inside the precipitation clouds. So before analyzing the data, we validated the radar reflectivity of the Cherrapunji radar by 2 individual methods. One is a comparison with the spaceborne radar on the GPM core satellite. Another is a comparison with the optical disdrometer, which was installed beside the Cherrapunji radar. The GPM core satellite on board dual frequency precipitation radar observed precipitation over the Earth between 55 degrees north and 55 degrees south. Because the GPM DPR is well calibrated, the data can be used to validate ground radars. Here we utilized double rad-lib software and compared the radar reflectivity of match-up data between the GPM DPR and the Cherrapunji radar. There were 6 opportunities to obtain the match-ups during the 2-month analysis period. We utilized the Cherrapunji radar data within 5 minutes before and after the satellite overpass, and also used the elevation angle above 3.3 degrees to avoid the ground crater. The right figure is the results. And the Cherrapunji radar underestimated the radar reflectivity by around 14 dBz. And we had to install optical disdrometer, possible 2, beside the Cherrapunji radar. And we have data during the analysis period. The radar reflectivity is the 6th moment of the raindrop size distribution. Therefore, the radar reflectivity can be validated by disdrometer. We used the PPI scan of the radar of 9-degree elevation level angle and calculated the average of radar reflectivity at around 1 kilometer distance. It corresponds to around 100 meters above the radar. The radar reflectivity from the disdrometer showed good correlation with that of Cherrapunji radar. And that result was consistent to the spaceborne radar. So that means that the Cherrapunji radar underestimate around 14 this DBZ. But there is a dependence of the reflectivity. The disrometer could compare over wider range of radar reflectivity than that of the spaceborne radar. Therefore, I used the obtained regression equation, this blue line, to validate the Cherrapunji radar. To produce the constant altitude distribution of radar reflectivity from PPI image of various elevation angles, we used a conventional method called Kressmann interpolation. This method uses the radar data within an effective radius and obtain a grid data from the sum of weighted average by the distance. The table shows the values selected at the weight coefficient in this analysis. The left figure shows an example of constant altitude radar images, and the observation date is 10th July 2019. The right top figure is Himawari 8 infrared images to check the larger scale cloud systems. And the right bottom figure shows the hourly rainfall at Cherrapunji. The daily rainfall of this date is around 400 millimeter. This sample is in the active rainfall spells of intraseasonal variation. So precipitation covers over the southern slope of the Meghalaya Plateau during the whole day. And also we can see two score lines passing through Cherrapunji from south to west. And tipping bucket linkage network can be used in our group. So these are used to validate rainfall, which Cherrapunji radar derived. The above 6 linkages are located along the ray, which are free from ground clutter. The 2 of the stations are India and 4 stations are in Bangladesh. The background figure is the average horizontal distribution of radar reflectivity during the 2 months. It shows the radar echo tends to increase with distance from radar. So it means necessity to calibration the dataset more. And the 6th graph are the scatter plots of the rain intensity between the rain gauges and the radar. The rain intensity was converted from radar reflectivity by zeta relation, which obtained from this disrometer observed at Cherrapunji. And we can see, so Tankaran Park and Braganj and Chatak and Nontaran has a relatively good correlation with Cherrapunji radar. But at Sirit, the radar severely underestimated rain intensity overestimated at Sirit. And this is the explanation of velocity azimuth display technique. It is one method to estimate airflow over the radar using Doppler velocity. If the airflow is uniformly blows over the observation area, the azimuthal variation of the Doppler velocity at the constant altitude shows sinusoidal curve. The amplitude and phase of the sinusoidal curve can be converted to the horizontal wind at the altitude. The estimation of the horizontal wind at each altitude of the 1 PPI scan can produce a vertical distribution of horizontal wind. So this figure is the vertical distribution of horizontal wind during the observation analysis period. Right panel is the meridional, left panel is zonal wind, and right panel is meridional wind. And the upper panel shows the radar-derived horizontal wind, and the bottom figure is ERA reanalysis data, ERA 5 reanalysis data. So we can, the radar data can reasonably derive the vertical distribution of horizontal wind. But unfortunately, it can observe only precipitating period. And we can check the synoptic condition during the analysis period. And during the 2 months, the southerly wind is dominant throughout the whole period. On the other hand, zonal wind has 2 regimes in the analysis period. One is the westerly wind regime, and another is easterly wind regime. And rainfall tends to occur during westerly wind regime, and it's also corresponds to the strong southerly wind. So this is a summary of my talk. So this is in this presentation we presented the initial analysis of Cherrapunji C-band radar data during July to August 2019, and we confirmed that the spaceborne radar can be a powerful tool to validate ground radars. But rain gauges and disdrometers surface measurement are also still important to know the real surface rainfall amount and to validate radar. And now the Cherrapunji radar is operated only PPI scans, and the PPI scans has a difficulty to know the precipitation just above the radar. Therefore, radar observation from the Bangladesh must provide another view of knowledge for the heavy rainfall area in the Meghalaya Plateau. And that's all. Thank you so much.
Thank you very much. So now it is open to the question and comments. So you have any questions, comments? Oh, so here's a question. Yeah, so it is coming from the Mahankumar Das-san. So I hear some, maybe you can talk this to Murata-san. Can talk?
Hello.
Hello.
Yeah, it's a very good study about the Megalayan plateau hotspot. So in your one slide, you had shown average of distribution radar reflectivity. Are those value annual or seasonal average? And is it radar reflectivity or radar reflectivity converted as rain rate in millimeter? Maybe 2-3 slide back.
Okay.
Average distribution of radar reflectivity. Yeah, this one. No, next. No. Another one.
Another one.
Next. Seasonal average.
Seasonal average. The first slide.
Just go. No. Letter. Letter. The Silet, Chatok, different values you had shown.
Okay. This one?
Yeah, this one.
So this is not the seasonal average. It's our observation. We can get through data set only 2 months. So this is average for 2 months in the monsoon season. Yeah.
So 2 months mean July, August, September?
Yes, July and August.
Okay.
Yeah.
Now understand. And the value you showed, Silet 1033 millimeter. This is reflectivity or reflectivity converted as rain rate?
Around 1,000, it's 2 months rainfall observed by rain gauge data.
Okay, great. Now understand. Thank you.
Yeah.
Okay, now, thank you very much. So do you have any other questions or comments? Then I have one. So you have installed your digital meter just besides the radar system. So is there any merit to install this digital meter just very near to the radar system? Maybe some problem also there, but there may be some merit also.
Conventional, we think if we so if we install the beside of the radar, the radar cannot get the near rainfall as it can get the rainfall nearby radar. So usually we will install some distance from radar. But in this occasion, we had the opportunity to install besides the radar. So I used the another I used I compared this metadata with radar data around 1 kilometer distance radar data.
So maybe we can get data from the radar somewhat above the ground, and so we can compare them. My question, idea is okay.
So sorry, ちょっと今。
Later we can discuss in Japanese language. So is there any other questions or comments? Nothing that here. Okay. Then now maybe we may approaching the time limit. So now we can proceed to the next speaker. Is okay? Thank you very much for our talk. And next speaker, I'd like to introduce next researcher, Dr. Kusela. He's an assistant director of the COMET program at the University Corporation for Atmospheric Research, UCAR, and leads the International Capacity Development Program. And he has over 30 years of research and weather application development experience in the field of hydrometeorology. So yeah, now introduce him. So please begin your presentation now. Maybe from USA.
Thank you very much. Let's see here. All right. Good morning, everyone. Good morning, good afternoon, and in our case here in the United States, good evening. So yeah, it's my pleasure to be able to speak for a few minutes on some of the work we've been doing in international capacity development, and I appreciate this opportunity. So for the past 5 or 6 years, we've been focusing on developing low cost observation networks to build capacity to really support flood, storm surge, and other kinds of monitoring using these low cost sensor networks. And I'll be talking about that today. All right, so just as a little introduction, a little background of our program, we've been focusing on developing 3D printed, so using 3D printers to develop a automatic weather station. This was launched to really address disaster risk reduction programs around the world. And the whole goal of this program is to design and implement a sustainable observation capacity in some of the least developed data sparse regions to really enhance and build those networks where there's very limited observations. Also to provide early warning observation capability to reduce risk for the most vulnerable communities, and then really provide this low cost, innovative, but also sustainable solution to support hydrometeorology related applications. So in terms of capacity development, we've really focused on using 3D printers along with other technology to make this project a success. So why 3D printers? First of all, in the past 10 years or so, they've become a very inexpensive but very valuable type of tool to build a variety of different types of sensors or other designs. We've integrated low cost, but based on our analysis, reliable microsensors that are relatively inexpensive, easy to find, and also have good reliability. One of the key designs of our project is design a system that actually can be printed, assembled, and fabricated, and then deployed locally in country. So building that capacity within the country itself. And the whole idea of using like 3D printers and microtechnology is that as any instrument that exists that's deployed out in the environment, eventually it will fail for a variety of reasons. So in this sustainable scenario, we can print and replace components as they fail to maintain that longevity and consistent data records from the different sites. And the whole idea is to really enable our local partners, like at the University of Dhaka, to really take ownership in building these and maintaining these observation networks. So I'm going to go through a little bit of the technology that we've developed, starting with our core system, which is the 3D printed automatic weather station. So it uses a variety of technology, uses Raspberry Pi single board computers, so inexpensive computers. We use 3D printing to build the housing. We have a 3-cup anemometer for wind speed. a wind vane for wind direction. We're able to measure light information, so UV, visible, and infrared. And then part of our design is a tipping bucket rain gauge to measure the precipitation rate in rainfall accumulation. We also have the state variables in a 3D printed radiation shield, so measures pressure, temperature, and relative humidity as part of the ensemble of observation measurements. It's typically these stations are put in remote locations without commercial power, so we have solar power backup, and then as much as possible, we try to set up the systems to transmit the data in real time, either through direct network connections, wireless to maybe a nearby wireless network, cell modem, which is probably our most frequent device, satellite communications, either using polar orbiting iridium satellites, GOES satellite over in the US, Meteosat satellites over more of the Africa and West Asia region, and also new technology, which is called LoRa, which uses long-range, low-power networks. So here's just to summarize, I mentioned all the different parameters that we measure. Here's just some examples of some of the designs and deployments that we've done around the world, shown in the images at the bottom. And just to highlight, as I mentioned, the systems provide real-time access, but all the data is also archived on the system itself. It can archive up to, we're up to about 3 or 4 years of 1-minute observations that can be stored on the system itself if there is no communications for backup. Data resolution is, we measure every 1 minute, but it's very flexible and adjustable so that you can adjust that time period. Say if you're only interested in 15-minute data, that's easily done. And I mentioned the different communication methods that we use. Some of the new and exciting developments that we've developed in the more recent years is there's been a lot of interest, including on our 3D printed automatic weather station observation, is to include air quality. So we've developed technology that integrates air quality measurements. So looking at particulate matter, ozone, volatile organic compounds, the different nitric oxides, sulfur oxides, methane, and carbon dioxide. Also included on the system that we have working now is a local lightning detection system, so that if you have a network of 3D PAS weather stations, you can then track and locate areas of convective weather within your network to really monitor for high impact weather events, heavy rainfall, and things like that. And one of the things I want to kind of focus on for this presentation is we've also developed a distance to surface observation system. So distance observation measures the height from wherever the sensor is down to the surface, and that surface could be, in most cases for our applications, looking at stream gauging. We're also looking at develop an adaptive system for storm surge monitoring, and we've also developed a system for snow depth monitoring. And snow depth, and interesting is that there's a lot of interest and concern about the water resources up in the snowpack, say in the Himalayas. This system can be basically integrated from the mountains down to the sea to really monitor all your water resources and monitoring for things like flood forecasting, storm surge, as I mentioned before. And it uses an ultrasonic sensor, which is another low-cost device in order to make these measurements. So just kind of go example. One of our examples here is showing the different configurations of our systems deployed for, on the left in the image on the bottom is for canal monitoring for water resources, irrigation. the system in the middle is on a river, be monitored for early warning, to say flood conditions. And then more recently, water resource management, the same sensor but redesigned, can actually then measure your snowpack. So again, measuring all these different areas of monitoring your water resources. In some of our most recent developments, we've adapted the same sensor now to do storm surge monitoring. Again, a low-cost solution that you're able to measure for along the coastal areas of the oceans or the seas, either for daily tidal monitoring, but more importantly, for when you have high impact events like this tropical cyclones, for storm surge inundation. So here's a couple examples shown here. One on the left is in the United States. The one on the right is a system deployed on the island of Dominican Republic. And really helps, the whole goal of these projects are really help with early warning of storm surge and prediction and evaluation. What's also been interesting as an application, it also helps with port operations on water levels for shipping in and out of the ports. And we've developed two systems. One has that you can also include not only sea level, but wind, and our kind of a more simpler solution just monitors the sea level conditions for storm surge conditions. Just kind of a status. We've over the years we've expanded to 12 countries, and I have a map there and I've shown the general areas that we're at now. Our first two stream and storm surge snow deployments have been here in the U.S. and Dominican Republic, as I mentioned. As part of this deployment and technology transfer, we provide extensive training. And what's exciting, COVID has slowed us down a bit, but our next deployment will be in Bangladesh. If everything goes well as planned, that we'll be able to provide the training and transfer this technology, so these networks could be started to be developed in Bangladesh with our partners at the University of Dhaka. Just wanted to show a few highlights going back to stream gauging, just kind of the data that we've been collecting. Again, going back to a stream gauge here in the United States, in the state of Colorado, or sorry, excuse me, state of North Carolina. Shown here that all the data that we collect for our stations up to this point are available in real time. And if you look at the web link above, this is the link to the real-time data for this station here in North Carolina. And then we provide a variety of observations. What I'm just showing here in that time series example at the bottom is the time series of stream gauge stage height. So all this data is collected and then put and made available in real time as an open data collection. Here's just the station in Virginia. It's primarily used for tidal monitoring, but also could be used for storm surge if a hurricane approached the east coast of the United States. This station, as I mentioned, has stage height and also has wind measurements. So here you can see the diurnal cycle of the stage height from the tidal variations at the bottom, but also there's a daily diurnal cycle of wind speed. So these two are closely related of the daily wind speed. There's also a directional relationship along with the sea breeze that comes in and out of this area here. So a lot of great information, measurements for monitoring for a very low cost to collect data for not only for monitoring for operations, but also for research. And here's just an example of the storm surge gauge, one of the gauges located in Dominican Republic. And you can see here, again, just looking at stage heights, and this is in a port. We also provide information on sensor health, for example, battery status, signal quality of the transmission. So you can also not only collect the data, but also make sure that your system is running properly and do this remotely and only have to visit the site if there's a problem. So just the last couple of slides, we've done some initial intercomparisons with reference sensors co-located with our systems. Here's an example going back to our station in the state of Virginia. It's co-located with USGS, so United States Geological Service tidal gauge, which is a system and right in the background of our station. So it's co-located by a meter or two. And just looking at the data, time series at the bottom for about 2 weeks, you can see again the diurnal cycle of the tide coming in and out, and it's captured very well with our low-cost station to the high-end research quality USGS gauge. You do see some variations, differences in the peaks in the tide, and at least based on this initial analysis, that our station tends to be underestimating the peaks in the daily tides in this region. And so something that we're looking at, and it'll be a continued area of research going forward. Going back to our stream gauge in North Carolina, again, in a comparison with USGS stream gauge. Again, in this case, you look at the time series of the data collected from this gauge. The USGS is in green, our station's in gray. And again, in this case, you can see that we really capture the variations in stage height from this river. You do see some small variations from our gauge itself, but what I consider in this case that we're actually seeing the higher resolution information of the variations of the river in this case. So we're very happy with the results up to this point, and we're excited to start deploying these in further areas around the world. So just to summarize, kind of going back to what I've talked about here in the last few minutes is that we developed these low-cost observation networks and these capabilities to really provide these innovative solutions to really help increase environmental monitoring. I briefly talked about our traditional 3D pod station, includes atmospheric monitoring, air quality monitoring, and then water level monitoring. And what I'm really excited about is using these observations, these networks, to support environmental applications, such as early warning, flash flooding, storm surge, inundation, and other decision support like water source management, agriculture, port operations, and a lot more types of applications. So with that, I will stop there, and thank you for your time, and please let me know if you have any questions.
Thank you very much. So very nice and very interesting. So I like to use your system. Yeah.
Oh, great.
Yeah. So is there any questions or comments on your side? There may be many. So from me,
I have one question.
Okay, yeah, please.
Question actually. Thank you for your very nice presentation. Actually, for meteorological observation system, it is very costly, and due to this cost, actually, that is the main barrier to increase the observing network in countries like Bangladesh. So if this type of low-cost instrument is available, then I think in Bangladesh also we can increase our observing network. And along Bangladesh coast, there is the 712 kilometer Bangladesh coast, but there is no surge gauge. But if we have this type of low-cost instrument, then we can install it along Bangladesh coast. So thank you for that.
You're welcome. Yes, that's one of our main goals, is to really expand those networks in regions like Bangladesh. And yeah, these low costs. I didn't really give a price, but they're on the order of about $300 to $400 each to make. I think the price hopefully makes it a lot easier to put out a larger network than the some of the more expensive traditional stations.
Thank you.
Thank you. Any other questions, comments?
I have one.
Okay, please.
I apologize. It was a very nice presentations. I have a couple of questions about that. So my first question is for the atmospheric data sensors that you guys using. Do you guys have any specific QA/QC method for validating the data that you collect from that? And my second question is there any scientific like paper or any research study has been published in any scientific journal that you can look further for knowing more? And my final question is for the, so you showed the different kind of sensors, but I like for the flood monitoring, I haven't seen any. Is there any specific sensors for flood monitoring available? I think that would be better for Bangladesh as well, because Bangladesh is a very flood-prone country. So just curious about to know about this stuff.
Yeah, yeah, great questions. The to addressing your first question, we have done and continue to do intercomparison measurements with referenced sensors, high quality sensors at calibration facilities to really get a sense of our data quality and reliability and calibration of our sensors compared to traceable reference sensors. And we're doing that with in collaboration with WMO. So that is ongoing, and we continue to do that as we build our database. In that regards, we do have an initial paper that's been published in I forget the name of it. It's like meteorological instrumentation, but we are working on publishing a couple more papers based on describing the overall design of the system and then the data quality. So yeah, so those are in the works. They're not quite published yet. And then the last question you had is the ultrasonic sensor that I discussed for storm surge monitoring and stage monitoring. It can also be used for flood monitoring. Actually, that's one of the key applications that we would like to use with that system is to use it for flood monitoring. And the idea with that is that as areas, rivers or other areas reach flood stage, or even before flood stage, they can send alerts to disaster managers, emergency managers, to let people know that there's conditions that might lead to flooding. So yeah, so we're working hard on building these applications. But yeah, great questions. Thank you.
Just a quick related question. So for the flood the sensors, do you have any locations in the United States? I have seen you have one at the Virginia and one at the North Carolina, but those are the floods monitoring system, as I suppose.
Yeah. So the idea, not the one in Virginia is for tidal storm surge monitoring, but the one in North Carolina is for flood monitoring. We do have another station in California.
Okay.
And that is also available, but we're those you can use those observations then when the rivers reach bankfall, that you have flood conditions and provide early warning.
In the East Coast,
West Coast are the two locations we have now, and we'd like to expand those to other places. So.
Okay, thank you very much.
You're welcome.
Hello.
Hello.
Hello. Hello, Professor Terao and Mr. Kamrul. Actually, I'd like to say thanks to everyone. And Paul, I think Paul and Elizabeth will visit Bangladesh soon, maybe in next 2 months. Is it, Paul?
That's our hope. Yes, they end of February. We hope to be there. Yes.
Yeah. Then to fabricate 3D poles in Department of Meteorology. And then I think we can arrange a meeting and call relevant stakeholders to meet you and learn more about your low-cost experiments. I think it will be a fantastic,
Good nice.
uh, and platform to share your low-cost instruments with our interested, organizations in Bangladesh. What do you think about it?
That would be a great idea. Yeah, I'd be happy to do that.
Okay, we will arrange a meeting. Thank you. Thank you, everyone. Okay, please continue.
Yeah, yes, I like to join from Japan, maybe, but internet, but maybe
Yeah.
good chance. Yeah, thank you very much. Yeah. Okay, so now we have a time limit already, so you may have some more, but I'm sorry, so we have to shift to the next speaker now. Thank you very much. And next speaker, I'd like to introduce the next speaker, Dr. Elizabeth Page, is the director of the COMET program. And now she's in the Boulder, so Yucca in Boulder, Colorado. And she's actively in training and capacity building activities with WMO and the Standing Conference of the Heads of Training Institutions committee. So now, please begin your presentation.
Thank you very much, Mr. Chair. Greetings to everyone from Colorado. And it's nice to see my colleagues from Bangladesh and other areas around the world. I'm very happy to be part of this conference and looking forward to talking to you about my title, which is Impact-Based Forecasting Communication Techniques and Training. I'd like to acknowledge my co-authors, Dr. Alan Bohl and Dr. Paul Kuchera, who just spoke as part of the COMET program. So in terms of impact-based forecasting, this is a new communication method that different national meteorological and hydrologic services are employing to help communicate their forecast information to their stakeholders. So it involves forecasting weather hazards and their impacts that they will have on society, as opposed to just forecasting on the actual parameters related to that forecast. Warning levels are based on vulnerability of the people in the area, and communicating warnings and potential impacts in simple language is the goal to the stakeholders and the public. So basically what we are trying to do with impact forecasting is move from what the weather will be. So for instance, 100 millimeters of precipitation in 24 hours or 50 knot winds, which we would then verify by observations. We're trying to instead move to what the weather will do. So talk about what the impacts are. So instead of talking about the amount of rainfall, talk about what the impact would be in terms of roads being flooded, communities possibly being cut off. With strong winds, you might talk about downed trees or power lines and the impact that would then have on the stakeholders or the communities, the general public, the first responders, whomever might be receiving that information. So it's a process of moving towards impact-based forecasting. Again, it's a matter of understanding what the impacts are. It is a matter of building partnerships with the different stakeholders and the people, the decision makers who are using weather data to make decisions about the safety of people and livelihood. So we talk about the weather impact risks of the hazards, the vulnerabilities of an area, and the exposure that to the society that could actually be harmed by these disasters. So the goal again is to change from what the weather will be to what the weather will do. So for instance, we could talk about a warning of heavy rain of more than 100 millimeters in 24 hours. And this example here is showing the region that would be affected by that rainfall. But for the people who are receiving that forecast of 100 millimeters of rain in 24 hours, they're thinking, what exactly does that mean to me? So with impact-based forecasting, we use the warning levels and give a little bit more information about what is actually happening with the forecasts. regions could have multiple warning levels. And in this example, we have the large yellow area and an orange area inside of it. And they correspond to the impact matrix, which is further here to the right, which is showing you both the impact and the likelihood. So for instance, area 1, which is an orange, corresponds to a significant impact with a medium chance of happening, whereas the area in yellow has a high likelihood of happening, but would have more minor impacts associated with it. And then what does that mean? So in part of developing an impact-based forecasting approach, these different matrices are put together. In this example, we're looking at the impact matrix for emergency management. So these are the impacts that emergency managers see under these different types of storms. So for instance, the two areas that we talked about, the yellow area had minor impacts and the orange area was talking about significant impacts. So the emergency managers take a look at that color coding and they can relate it to this impact matrix and learn more about what would be expected in terms of impacts with this event. And then along with that, there is a response matrix that comes along with this, which talks about how do we communicate those impacts to our stakeholders. So for instance, this color coding where we talked about area 2, which was a larger area, that had a, that corresponded to this low response matrix where we're basically asking people to be aware. And there's some different types of wording that go along with that. Whereas the medium was talking about being prepared. So this has a slightly elevated tone to the communication that then goes out to the stakeholders and the general public. So in the US, we have developed the Weather Ready Nations program in cooperation with the USAID and the National Weather Service International Activities Office, and in partnership with the Hydrologic Research Center. This is an approach to impact-based forecasting, which is based on the WMO publication 1150, which are the guidelines for multi-hazard impact-based forecast and warning services. And the second volume of this guidance was just published this week, which talks about putting it into practice. So these are the two references at the bottom of this slide. So part of the impact-based forecasting implementation has been conducting a series of workshops. Some of them are training workshops, some of them are actually workshops geared towards implementing impact-based forecasting. So we have gone from workshops in person, where we had a limited number of participants that we were reaching with each of those workshops. And then this became very difficult during the COVID-19 pandemic. So now we've moved to virtual workshops. And with these, we've taken more of a blended learning approach. And for anyone who's been teaching during the pandemic, understand what it's like to try and do an online course versus an in-person course. So what we have done is developed different e-learning resources that are on the basics of impact forecasting. And then we've done in-person workshops, not in-person, sorry. We've done live workshops or synchronous workshops with blended learning activities. And the screen capture I have here was actually from a workshop that Paul and I were working this week with a group. So with training delivery, moving into this idea of a blended learning approach, and also the idea that not every country can have a workshop and be trained through the live workshops. We have developed online e-learning resources so that we can reach a greater audience through our METED website at Comet. So we have a series of e-learning resources that include videos, that include e-learning activities, which include simulations, so that we try to put the person who's taking that lesson in the shoes of the decision maker and to make decisions and see what the outcomes could be of different types of decisions. And along with that, as I mentioned, we have blended workshops where we're using these online modules as the prerequisite material and then having synchronous sessions. And during the sessions, we have interactions so that the instructors and the participants can work together. And we work through exercises as well as case studies. And so the second diagram, whoops, sorry. The second diagram at the bottom is a polling question that we've been employing during our synchronous sessions so that we can see how all of the participants are absorbing the material and they have a chance to discuss different case studies and discuss different points of view. And we get excellent different analyses of the same situation. It really helps others learn through looking at other people's perspectives on how they forecast and how they communicate the risks with different weather and natural disasters. So this is a list of the training resources that we've developed. These are the online lessons. We are working towards a full curriculum related to implementing impact-based forecasting. And we've been working with the WMO on these competencies and how they could be used internationally. So the online resources vary from the actual process of implementing impact-based forecasting to the idea of using these forecasting services, how communicating risk is done, how we can build partnerships through this communication, and then how the actual activities are done in terms of implementing it. So things like the identifying hazards and constructing impacts tables for both Met services and for the stakeholders. And again, communication is critical at this point, and the forecasters need to be talking with the disaster managers or emergency managers, the different groups who are making decisions, perhaps relief workers or different groups that come in after the hazards. All of these stakeholders are important to have a strong partnership so that you understand what the stakeholders need, and so that the proper, not only proper weather information can be delivered, but it can be delivered in a way that they can use it in their activities. So that's all that I have for this presentation. Thank you again for the opportunity to talk at this conference. I really appreciate it.
Thank you very much. And so now we can discuss. And so please raise your hands or talking directly. Please you have your questions and comment now. Yeah, there's one question to the chat. So from the Chaki-san. So can you talk now? Voice. Dr. Shuchi Chaki, can you talk?
Can you help me? I can't see the chat window right
you.
now.
Okay. Yeah, please.
Thank you very much. And yes, I got very much benefited from the comment platform. So I really want to express my gratitude, actually. I have no question
so
in particular, but it's just, I just want to express thank you. So,
I appreciate that. Thank you very much.
Yes, now already working very nicely in Bangladesh, maybe. Thank you very much. And so is there any questions, comments? So I have one. Okay, so I'm from Japan. And so Japan also have many struggling about that, the disasters. So we are also defining some 5 classes of that, the warning level or something like that from the Japanese Meteorological Agency. They're doing many talks about that. So do you have any information about the Japanese experience like that? So how they are constructing that system for the evacuation or the warning system, something like that? Some information.
I'm not familiar with how, I'm not familiar with the Japanese implementation of the process. I would like to learn more though, because it's very interesting to see how different countries are impacted and how they arrange their levels. I know that in the Philippines also very subject to very different types of disasters, and they have several levels that they use to be able to show the severity of the situation to the people who are receiving that information.
Maybe it's very important for my side also. We may discuss and exchange ideas in
Yes.
future. Yes, thank you very much.
Yes.
And also,
Yes, absolutely.
I'm impressed by your colorings for the warning levels, and yellow and orange and red. So it's your system.
Yes.
In Japan, yellow, red, and violet.
Violet, yes, yes.
And after that, black.
Yes. You need, yeah, more levels because of the severity of the potential events. Yes.
Yeah, interesting. So
Yeah, I would like to see more about that.
Yeah. Thank you very much. Yeah.
Thank you.
Oh, is there any questions, comments?
I have one comment.
Yeah, please.
Actually, Elizabeth, I am working in Bangladesh Meteorological Department. So in Bangladesh, we are going to implement impact-based forecasting. In fact, today there is one workshop, and after finishing this seminar, I will join that workshop. Your presentation will be a good reference and good, it will be very helpful for me for implementation of IVF in Bangladesh. And
thank you so much.
Yes, and I will also in future I will also contact with you about IVF. And thank
Wonderful.
you for
Thank
your
you.
nice
Yeah,
presentation.
Thank you. I look forward to hearing more about what you do with your implementation. Thank you so much.
Thank you.
All right. I believe you're muted.
Sorry. Yes, I'm muted. So now, yeah, please make a question. We have some time, more time, so please. Is there any questions, comments? Okay, now? Okay, then thank you very much for your nice presentation. Now, thank you very much.
Thank you.
So now we already had a full talk from speakers. So now the program going to the concluding remarks. So Kamara-san, can we say something here? Maybe?
Yes, actually, firstly, I want to thank all four presenters in this session. And for meteorology, actually, observation is very important. And as I mentioned earlier, that instrument for meteorological observation, that the cost of instrument is very high, and it is the main barrier to that widely installed meteorological instrument in countries like Bangladesh. So it is very important. That was one presentation. It was very important that low cost instrument is available. Then for new technique or new tool for using in meteorology, that means prediction of or use in forecasting, that also very important, which we already that already presented by Dr. Nachiketa Acharya and Murata-san. And then all forecast or warning is generated, then it needs the proper dissemination or proper utilization. And impact-based forecasting is very important for countries like Bangladesh. So that presentation from Elizabeth was also very important. And lastly, that warning should go to the end users in time. That means with sufficient lead time. Otherwise, there is no meaning. If your warning or your forecast is very correct, but if it not goes to the end users in time, or with value added forecast not goes to the end users in time, then it is useless. So that also very important. And I also thank to all participants, all presenter again, and thank to all of you. Thank you.
Thank you very much. So I like to close this session, and I feel all the same as Kamaru-san. So we have a very nice session with very wide aspect of the research and disaster prevention, our subjects. And so from that, the observation and also the statistical analysis, and also that the system for the evacuation from this dangerous situation also discussed. And we are focusing on the different type of meteorological hazards. So that rainfall has to be analyzed, and we have to know the system and the mechanism how they occur. So in this sense, the radar in India is very important for Bangladesh situation also. So we have to have some international collaboration for that type of research, so we can aware about that. So, and also we have many audience, and so many active discussions also done here. So thank you very much, and thank you all. Now we can close this session. It's okay. Thank you very much.
Thank you, all of you.
Somewhere, yeah.
Thank you to both Dr. Terao sir and also Kamul sir for nicely conducting this session. And I also like to congratulate and our heartiest gratitude to all the participants, Dr. Nachiketa, Dr. Murata, and both Dr. Page, Elizabeth Page, and Dr. Paul for their nice presentations and talks, and also the cordiality they maintained for the conference. We are really grateful to them, and also to both Terao sir and Kamru sir. So I'd like to thank all the participants who joined in, also participated in throughout the chat box, and also by raising hand and asking questions in person. I thank all of them. So this is the end of this technical session 4. Our next technical session 5,